Hello and welcome back to PyMan Tutoring. Today we're going to be talking about functions, domains, and ranges. Let's begin. We'll begin by looking at function notation. Now you've been used to seeing equations like y is equal to 3x squared plus 2x plus 4, some simple quadratic expression. We're now moving into function notation where instead of using a y, we will use the function sign curly f of x. And this doesn't mean f multiplied by x, it means a function which is converting values of x coming in into some kind of output. And it's useful to think about this as a function box of some kind. Some black box, we're feeding in values of x, and then out of the other side comes the function of x, which in this case is the quadratic 3x squared plus 2x plus 4. So a value of x is fed in, let's say a 1 is fed into this function, and what comes out the other side is 3 lots of 1 squared plus 2 lots of 1 plus 4, which is just 3 plus 2 plus 4, which is 9. So this function has the effect of taking an input value of 1 and converting it into an output value of 9. And so we can write that f of 1 is equal to 9. That's function notation. And now we talk about what kind of values of x we are allowed to feed in to this function. And that range of values is called the domain of the function. Similarly, there will be some set of values that can come out of the function, and we refer to that as the range of the function. So this is the independent variable going in as x, and what's coming out is the dependent variable. Let's now take a look at what mathematically distinguishes a relation from a function. So here we have a set of 4 pairs of numbers, and each pair represents an x value as the input and a y value, or an f of x value as we now call it, as the output. And the question is, does this set of paired numbers represent a relation or a function? Now we can draw a diagram showing the domain of this function, i.e. the range of input values. We have a -3, we have a -2, we have a -2 again, so we won't list that twice, and we have a 5. These are our input values. This is our set of output values. So over here is the range of the function, and over here is the domain of the function. So where does each of these input values map as we apply the function f to it? So -3 maps to the value 4 in the output range. 5 maps to the value -3. But -2 we see maps to 2 different places. It maps to both a 1 and it also maps to a value of 7. And when a given input can produce more than one output, we call this a one-to-many relationship. and this is a relation. It basically means that when you feed your number into this black box, this function, you cannot be sure what's coming out the other end because there's more than one possible output. If there's more than one possible output, it is a relation. For a relation to be a function, the input must guarantee a certain output. So for example, if this -2 had been a, let's say, -4, for example, then we would have had a -4 uniquely mapping to the value of 7. This particular line would disappear, and we would now have a one-to-one relationship between the input and the output. And now we would have a function. It's also possible to have a many-to-one relationship and still be a function. So many to 1 is a function. 1 to 1 is a function, but 1 to many is a relation. So for example, in this top case, we can have two different values of input producing the same output. Let's look at an example of that. So again, using the above set of values, let's suppose we have the -3, 4 still, and the -2, 1. Now let's suppose we have -4 producing a 7, and let's suppose we have a 5 producing a 7. So in this case, we have two different input values producing the same output value. And that's okay. That's still a function. That's a many-to-one relationship, which means that we have a function. Our domain is -3, -2, -4, and 5. Our range of values for the output is 4, 1, and 7. And we can see that the -3 maps to the 4, the -2 maps to the 1, -4 maps to 7, and 5 also maps to 7. The key thing is that given a certain input value, x, we know exactly what output value we're going to get. Even though two different inputs are producing the same output, we can guarantee that a -4 going in produces a 7, and we can guarantee that a 5 going in produces a 7. If we have a guaranteed output, that means we have a function. Another way to think of this graphically is with what's called the vertical line test. So let's look at that. Now we said that in order for a relation to be a function, a given input value of x must produce a known output, f of x or y. So this means that for any particular function, let's just put some random function here, and this means that when I feed in a certain value of x, I must produce one and only one value of f of x. And what that means is that if I draw a vertical line through the function, it's only allowed to cross that function at one location, and that's called the vertical line test. And so, for example, obviously a linear function passes the vertical line test. A parabolic function will pass the vertical line test. Cubic functions pass the vertical line test. So what kind of function doesn't pass the vertical line test? Well, let's take this function, for example. Here the vertical line clearly passes through two locations. So if I choose a particular value of x, I don't know if I'm going to get this value of y or this value of y. And therefore, this is a relation, not a function. A circle, for example, x squared plus y squared equals radius squared. You might think this is a function, but for any given value of x, my vertical line crosses the circle in two locations. So this is not a function. Now the one that confuses people a lot is when y, or we'll call it f of x, is equal to the square root of x. And you may be used to thinking that, for example, if y is equal to 9, then the square root of y would be plus or minus 3. 3 squared gives 9, negative 3 squared gives 9. And so you may have seen the square root function drawn in this fashion. So here is 9, square root of 9 would be 3, square root of 9 is also negative 3. And so you might look at this and say, well, this is not a function. It fails the vertical line test. But the square root is a special case. When we write the square root of x, we are implicitly saying the positive square root of x. So we're putting an implicit limitation on the range of the function. We're saying that we only accept positive values of the square root. And so this is my graph of y equals the square root of x. And it is a function under these conditions. And this is why when we're doing the quadratic formula, we show plus or minus the square root of b squared minus 4ac. We explicitly list plus or minus in order to remove any ambiguity about what we're using in that formula. We are actually using both the positive square root and the negative square root. But if nothing is written in front of the square root, it's implicitly understood that we're talking about the positive square root of that value, and therefore we have a function. So we say that y equals the square root of x is a function. But conversely, y squared equals x is not a function. And you might say, well, hang on a moment. If I just take the square root of each side of this equation, I get y on this side. I get the square root on this side. How is this not a function? Whereas we know that y equals the square root of x is a function. And again, it comes down to because by taking the square root here, this should really say plus or minus the square root. And if we have plus or minus the square root, that is not a function. So in this first case above, we were given y equals the square root of x, no plus or minus signs, and therefore there's an implicit restriction on the range of the values of y. Conversely, in equation number 2, we start off with no square root signs, so there is no implicit limitation on the range in this case, and therefore when we do some algebra on it to make equation number 3, we're not allowed to introduce new restrictions that didn't exist in the original equation, and therefore we must include both the positive and the negative square root, and therefore this is not a function. So be careful with that. It can get tricky. Let's look at a similar case. Let's suppose you're given y is equal to the square root of 25 minus x squared. Now the first thing to note is you've been given the square root as part of the description, and therefore this means positive square root implicitly. And therefore this is a function. And what does it look like? Well, let's try to quickly sketch it. Always useful to sketch these functions to make sure that you've correctly determined the range and domain. So we know that when x is equal to 5, y will equal 0. And we know that when x is equal to minus 5, y will be equal to 0. And if x is equal to 0, y will be equal to the positive square root of 25, which is 5. So what we actually have in this case is a half circle. We only have a half circle because of the implicit understanding that we're dealing with the positive square root. Now, what about the inverse function? Well, for the inverse function, remember we swap x and y. So now we write x is equal to the positive square root of 25 minus y squared. And because we are saying the square root is positive, we are implicitly saying that x must be greater than or equal to 0. So let's rearrange this equation. We can square both sides. X squared is equal to 25 minus y squared. Still remembering that we have the limitation that x is greater than 0. And finally, we can write x squared plus y squared is equal to 25 with x greater than or equal to 0. So what we have is the equation of a circle of radius 5, but with a restriction on the x values. So what does that look like? Well, a circle of radius 5 put in those 4 points. circle of radius 5 with x values greater than 0. So that means I've only got the positive x half of the circle. And this makes sense because if you remember, when we do an inverse function, what we're really doing is reflecting that function in the y equals x axis. So we draw a line here, y equals to x. And if you imagine reflecting this yellow function in this line, we will end up with this piece down here will reflect up to here. This piece up here will reflect down to here. And this piece over here will reflect down to here. So we do indeed end up with the right-hand half of the circle when we do the inverse function. Now, is the inverse a function? Well, it fails the vertical line test. If we look at this right-hand diagram, draw a vertical line, crosses in two locations except right at the edge here. So this is not a function. So it's quite possible for a function to become a relation when you do the inverse. What actually happens is that the domain and the range have swapped places. In this first diagram at the top, we see x lying between a positive 5 and a negative 5, and the y values, or f of x, lie between 5 and 0. Now over here on the second diagram, the inverse function, these two sets of numbers are reversed. So the x values lie between 5 and 0, and it's the y values now that range between 5 and negative 5. So remember, when you do the inverse of a function, the range and domain swap places. Now let's say a little bit about set notation and the way that we write down the domain and range of a particular function. The way we write domain, we use a capital D for domain, and we say that is equal to, and then we use curly brackets to mean the set of things. We're talking in domain about the x values, and so we're going to write down some restrictions on the values of x. Now, if x can range all the way from negative infinity to positive infinity with no restrictions, we say that x is an element of or belongs to the set of, and then we use this symbol, r with two vertical lines, to mean x belongs to the set of all real numbers. It can be any real number we like. We close the curly brackets, and that defines the domain. In our previous example, we had discrete values of x. And then we would just simply write the x values separated by commas. So for example, 2, 3, 5, negative 4. If these are the only values of x which are allowed, that defines or the domain of x. And now for the range of the function, we use a capital R, and we use the same kind of set notation. So if there's no restrictions on the values of y coming out of the function, we can say that y is an element of the set of all real numbers. And that would be our range for an unrestricted function. Now, it's quite possible that we have some restrictions on the values of either the domain or the range. Let's look at an example of that. Let's suppose we have the parabolic function y is equal to minus 4 x minus 3 squared plus 2. And you may recognize this as a vertex form of a parabola. The vertex occurs at 3, 2, 1, 2. So there's my vertex. And we have a negative coefficient in front of the x squared. So we know this is pointing down. So we have a parabola that looks something like this. And it's continuing on down to negative infinity. So what does the domain and the range look like in this case? Well, we can say the domain is the set of real numbers. Now, are there any restrictions on the value of x? As we continue down in this direction, x is going to just keep moving to the left towards negative infinity. And on this side, it's just going to keep moving to the right towards positive infinity. So the domain is unrestricted. And so we can close the curly brackets, and that is our complete domain. Now, what about the range of values? What values of y am I allowed to have? Well, y can be any real number, as usual, but we have a restriction because clearly y never goes above the vertex here. And that vertex occurs at y is equal to 2. So we have a restriction, and when we have a restriction, we put in a vertical line, and this vertical line means such that. So y belongs to the set of all real numbers such that, and then you put the restriction. Y is less than or equal to 2. Close the bracket. Let's look at a couple more. Okay, here we have the graph of x squared plus y squared equals 49. X squared plus y squared is r squared, so that's a circle of radius 7. We know this fails the vertical line test, so it's not a function, but that doesn't stop us from defining a range and a domain. So first of all, the domain, which means what values of x are we allowed to have? And so x belongs to the set of real numbers such that, now what's the restriction on x? Well, x has to be less than or equal to 7. It has to be greater than or equal to negative 7. So there's my domain. And the range is very similar, except we're talking about y values now. Belongs to the set of real numbers. Real numbers just means counting numbers, decimals, everything in between, any number you can think of, positive or negative. And the restriction here is that y must lie between 7 and negative 7. What about this one? Y is equal to 1 over x minus 3. So we recognize that on the bottom we have the possibility of a 0, and therefore we have a situation with an asymptote. Let's quickly draw what that looks like. So when x is equal to 3, this function blows up to infinity because we're trying to divide by 0, and therefore we have an asymptote at x equals 3. And if you feed in values slightly above 3, you'll find you are positive and very large. So the graph looks like this. And if you feed in numbers slightly below 3, you'll get very large negative values. And so we know that the graph looks something like this. And as x tends to positive infinity, we get closer and closer to 0. And as x tends towards negative infinity, we will get closer and closer to 0, but from the negative side. So domain and range, let's think about it. So domain, what values of x are allowed? Or x can be any real number, but it's not allowed to be equal to 3. And that's how we write it. And what about the y values? Well, the y values span from negative infinity to positive infinity. So y can be any real number, but y never actually reaches 0. So y is not equal to. One last point to make is if you have multiple restrictions on a particular function. So let's look at something that has multiple restrictions. Suppose we have a couple of asymptotes. Let's suppose we have a function that does something like this, and something like this, something like this. And let's call this 5. So how would we write the domain and range of this particular function? Well, domain is all the possible values of x in curly brackets. So x belongs to the set of real numbers such that, now we can see that we have asymptotes at 0 and at 5. So we can write x is not equal to 0, or we want an or. So we can either write the word or, we can put a comma, or we can use set notation for the union of two things. All of those are acceptable. X is not equal to 5. And for the range, we have that y is a member of the real numbers, but y is never equal to 0. So let's finish off with a quick example just to solidify some of these ideas. Let's say we have 3x plus 2y squared is equal to 4. And the first question is, do we have a relation or a function? And as I said earlier, sometimes the best way to determine that is to sketch the graph. Let's make a small table of values. Rather than x and y, let's do x and y squared. The reason for that is because we don't want to introduce any ambiguity about the square root yet. So when x is 0, feeding into the equation, that means 2y squared is 4, and therefore y squared must be 2. If we feed in a value of x of 4 over 3, multiply that by 3, you get a 4, and that means that the 2y squared must be 0. So y squared is 0. If you feed in a value of 5 for x, side, so 2y squared would have to be a negative number. That's not possible, so that does not exist. And if we feed in a negative 1 for the x value, we would get 2y squared is equal to 7, and therefore y squared would be 7 over 2. Let's see if that's given us enough points to plot this thing. When x is 4 over 3, y squared is 0, so that means y is 0. So 4 over 3. And when x is 0, y squared is 2. Now, if y squared is 2, that means that y must be the square root of 2, plus or minus. Because over here, y, which is positive or negative square root of y squared, remember? So we get plus or minus 2 here. And here we would get plus or minus square root of 7 over 2. So basically our relation is doing something like this. And I think, as you can see, this clearly fails the vertical line test. So this is not a function. What about the domain and the range? Well, let's write those over here. So the domain, what values of x are allowed? Well, x can be any real number such that x is less than or equal to 4 over 3, because we don't have any x values higher than that. The range, the y values, can be any real number. Oops. And as you can see from the graph, the y's are heading more and more positive on the top half, more and more negative on the bottom half. There's no restriction on y at all. And so y is just a member of the set of real numbers. Now, part 2 of the question is, what about the inverse of this, what we now know is a relation? What about the inverse of this? So let's take a look. If we do the inverse, we're going to change the x's to y's and the y's to x's. So we'll end up with 3y plus 2x squared is equal to 4. And now if we rearrange that, we can get y is equal to 4 minus 2x squared, all divided by 3. And now let's see what that looks like. Well, you probably recognize that as a parabola with the coefficient of x squared being negative in here, which means it's pointing down. So what this actually looks like is something like this. And remember that we could have determined that graphically by reflecting the original function in the y equals x axis. So if we draw the y equals x line here on the original relation and we use it as a mirror, we will actually produce this inverse function down below. So clearly this passes the vertical line test. And remember that when you do the inverse of a function, you expect the domain and the range to change places because what you've done is swap x and y. So now the x values can range anywhere from negative infinity to positive infinity, no restriction, and the range now y belongs to the real set of numbers such that now y is less than or equal to 4/3. So there you go. That's functions, domains, and ranges. I would say really the tripping point to watch out for is that square root function. Remember that if you are given a square root in the equation, then it's implicitly just the positive square root. Whereas if you create a square root in the function by doing any kind of algebra, then you must include both the positive and the negative values of the square root. That's it for now. Don't forget to like and subscribe. Press on the bell if you want to get updates for new videos as I post them. Thanks very much.